Hi, this is lecture number 47 on subsurface drainage design. We will continue the subsurface drainage design. So, in this from the previous lecture using the Hooghoudt equation. So, there is an example. So, determine the required drain spacing for the basic design criteria Q, which is a recharge or the drainage discharge, which is equal to 7 mm per day, and H is 0.6 meter. So, that is we are expecting the highest water table at the center of the two drains is 0.6 meter, and pipe with outer diameter is 0.2 meter, and U, which is equal to 0.3 meters, that is vector parameter or perimeter. Okay. So, schematically you can see. So, this is the two drain pipes, right, and so W, that is the base, from the top to the base is a 1 meter, and D, capital D, which is from the base to the impervious layer, that is 3 meter, and you have to find out drain spacing. There are two layers. So, the top layer, that is 2 meter per day, and bottom layer hydraulic conductivity is 1 meter per day. So, with this find out what is L, the drain spacing. So, we need to bring the Hooghoudt equation and then the criteria into the picture, and using the trial and error method we are going to find out the length L. So, let us see this. So, here, so the first trial, let us say L is equal to 40 meter and D which is equal to 3.0 meter and U is equal to 0.3 meter. So, these values are given from the previous example, right, and previous slide. So, if you see this equation, right. So, this is Hooghoudt equation and these are the conditions. Okay. So, L is equal to 40. So, when L equal to 40, so L by 4 will be 10, okay, and your D is 3.0. So, since D is less than L by 4, so we are going to use this equation to find out small d. Okay. So, that is here. So, you are going to find out small d. So, pi into D 40 by 8 ln. Okay. So, this is supposed to be pi not this is not D. So, this should be 3.0, this is D. Okay. So, then putting the values you get small d is 2.15 and L square, and now you substitute that into the drain space formula, that is L square 4 k 1 h square by q, and you get L as, this is L. So, L as 34 meter. Okay. So, if you see the initial guess was 40 meter and after calculation you get 34 meter. So, this L and the initial guess L, they are not the same. So, what we are going to do? We are going to we are going to see another trial by putting L equal to 34. Okay. So, that is the next trial with L is equal to, so let us say L is equal to 34 or even 32. So, close to that. So, this is second guess. So, now L by 4 is that is 8, but still it is less than, right, less than, D is less than L by 4, and we are going to use the same equation. Okay. And this is supposed to be 3 meter, okay, and you get 2 meter small d, right, and then finally you get L is equal to 33. So, the final solution 33, the initial guess is 32, they are very close. So, you can take L as 33 meter here. So, that is the solution for drain spacing, okay, drain spacing, that is L equal to 33 meter. So, the same problem can be solved using the graphs. So, that is called graphical solution. We can also see the graphical solution here. So, how this is different from the analytical solution. So, here the two things, the first number one is you have to find out 8 k 2 h by q and 4 k 1 h square by 2 by q. So, these two terms if you substitute the values, so one is 457, 183. Okay. So, either you use this one or this graph or this graph. So, since we already see this thing as around 30, 32. So, let us consider the graph B. So, in the graph B, if you see 8 k 2 h q, that is 457. So, 457, that is already there, and similarly for 4 k 1 h 2. So, this is another one, okay, 2 points, and d is equal to 3, right. So, this is d is equal to 3. Okay. So, and then you follow the line and see this is exactly hitting this point, okay, and the corresponding, this is the line. Okay. So, this is 30 and 35. Okay, that is a drain spacing. It should be between 30 and 35. So, if you do the interpolation, linear interpolation, you get L is equal to 33 meter, which is almost same as the previous solution. Okay. So, there are some notes on Hooghoudt formula. So, if you observe the formula, Q is equal to 8 k 2 d h by L square plus 4 k 1 h square by L square. So, the spacing L. So, the same thing you write down like this, L square is equal to 8 k d h by q plus 4 k h square by q. Okay. So, when do you expect L to be increased? So, when you have the k increase, right, k increase, L is going to be increased, and q decrease, right, q decreases, then also L is going to increase, and capital D increases. So, less influence when L is small, right, capital D, that means you are coming here. So, the capital D increases. So, that means D is going to be increased. So, capital D increases, D is going to be increased. Okay. And then H also increase. Suppose you are increasing the H and L is going to increase. Okay. So, these are observations from the formula. So, that means what is the influence of this? What is the what indication you are going to get? For example, so if the soil is permeable, so it has hydraulic conductivity. So, that means you can increase the spacing line, lateral spacing in that case. So, if you are expecting less Q, right, the drainage discharge is low from the area, right, low from the area. So, then or the recharge which is taking place is low, then you can also increase the lateral spacing. Okay. So, H increases. So, H increases in the sense, so vertical flow is increasing, right, vertical flow is increasing. So, in that case also you can increase the line spacing. So, and simple Hooghoudt formula. So, in this equation what happens, you can you can eliminate still the water flow or horizontal flow above the drain. So, then you are left with the horizontal flow below the drain. So, that is L square into 8 k d h by q. So, this is simple Hooghoudt formula we call. So, this is useful when h is smaller, okay, or the stratum below the base is more favorable to drain. So, you have this is the base, right. So, below the drain has more favorable to the drain, that means suppose K 2 and K 1. So, K 2 is more than K 1. So, then the top is less permeable and bottom is permeable. So, you get the horizontal flow at the bottom. So, where a significant vertical flow is to be expected and relevant flow zone has a very low hydraulic conductivity. So, instead of H, it should be used to Hooghoudt equation. So, suppose vertical you have vertical flow is dominating, right. So, in that case, so the H will be considered as H minus H v. So, that is you have to include H v also into the picture. Then the limitations here, the Hooghoudt equation assumes an elliptical water table. If you see the water table, so I have been drawing several times. This is elliptical water table which is occurs below the soil surface. This is what the Hooghoudt equation assumes. But what happens? So, if the water table is just rising up, right, rising up and accumulating the water on the top surface, just like here if you are seeing. So, then Hooghoudt equation has a limitation in this kind of scenarios. So, the streamlines will be concentrated near the drains with most of the water entering the soil surface in the vicinity. So, in this case what happened? So, most of the streamlines will be concentrated because it is a ponding on the surface. So, most of the this will be concentrated near the drains. Okay. So, this is one limitation, and the next is estimation of equivalent depth. So, this is very important when the Hooghoudt consider the pipe drainage system to a deep ditch system by introducing the equivalent depth concept. So, equation of equivalent depth dE, the Hooghoudt has given this formula, the pi L by 8 ln into L by pi r naught. Okay. So, and Van Beer's equation, so that is equivalent depth is estimated with ds by 1 plus 8 d by pi L into 8 ds by pi square into r naught. Okay. So, where the ds is the thickness of the aquifer below the drain level. Okay. So, ds is the thickness of the aquifer below the drain level. So, below the drain level. Okay. So, then Moody also has given an equation for equivalent depth. So, which is d by 1 plus d by L 8 by pi ln of d by r naught minus 3.4, and he has two conditions. So, 0 d by L less than or equal to 0.3 and d by L greater than 0.3. So, based on these two conditions, so dE will be estimated with different formulas. Okay. So, r naught is the radius of the drain and d is the drain depth. Okay. So, then ds is the thickness of the aquifer below drain level. So, then there is a Donon's formula. So, Donon's proposed the following formula for parallel drain spacing. So, this is L square 4 k by q into d plus h square minus d square. So, this is almost by solving the algebraic functions, and if you look at the Hooghoudt equation and Donon's equations, they are almost similar, right, 4 k q d plus h square minus d square. So, this results in the same formula, but only thing here this will be equivalent depth. Okay. That is the drain depth. So, then let us revisit Ernst's equation. So, it is applicable for two layered soil profile having different k values. So, if you remember the Hooghoudt equation, we have k 1 and k 2 based on the drain which is installed exactly like the base, right. So, which is above k 1 and below k 2, something like that. Okay. So, Ernst's equation will be work for the two layer system, and the position of the drain level may be above or below the interface of the two layers. Okay. It considers the radial flow of course, the Ernst equation considers the radial flow and kT less than kb. So, this is kT, this is the top and this is the below, right. So, in this case kT is less than kb, right, less than kb. So, that means the vertical, the vertical head will be almost negligible, and mostly the flow is taking place either horizontal or radial, okay, in this case. The application of Hooghoudt equation, it is applicable for homogeneous soil for 2 layers soil system having different k values, okay, the similar to Ernst equation. So, this is also applicable and the drain level coincides with the interface of the 2 layers. Okay. So, it does not allow radial flow towards the drain, that kT which is greater than kb. So, in the Hooghoudt equation, the top layer is more permeable than the bottom layer. So, in case of Ernst equation, the total hydraulic head required H is equal to vertical, horizontal and radial. Okay. So, that if you combine all these, the vertical, horizontal, radius. So, this equation looks like this. Okay. This is the total equation, Ernst equation, and where d naught or d naught plus d 2. So, here there is a schematic, this is open ditch system if you see, and this is the drain water table, this is the water table, and there is a horizontal, look at this is the k 1, right, this is the 2 layers k 1 here and k 2 here, the 2 layers here. So, drain is installed above k 1, okay, or the layer 1. So, from the drain bottom, so this is the dV, dV indicates the thickness of the layer through which vertical flow occurs. So, vertical flow will be concentrating in here, right, whereas the radial flow concentrating from here to the top layer, right, only within the top layer, and the horizontal like dH. So, dH is concentrating in the both layers, that is the k 2 and k 1, okay, so from this point to this point, all right. So, these depths are very important, and y is the water level in the drain, y is the water level in the drain. Okay. So, then dV is the thickness of the layer through which vertical flow occurs. So, d naught or d naught plus d 2 and dr which is less than L by 4. So, dr the thickness of the aquifer through which radial flow is taking place will be less than or equal to L by 4. Okay. So, with this concept let us explore the other details. For example, if you see the previous, this thing. So, here basically ADR, right, in this formula this is ADR and mu. So, these are very important, and we are going to discuss how do you estimate the ADR and mu in the following slides. So, here about mu. So, mu is the pipe drain run half full basically. So, in that case, so since the pipe drain is half full, that is the assumption. Okay. So, in case of circular, you get u as half of the perimeter, half of the perimeter of circle. So, that is pi r naught. So, if this is r naught, so this is the one. So, where u is the wetted perimeter of the drain, A is the geometry factor of the radial resistance that we are going to estimate. Okay. So, let us find out. In the previous week I discussed on how to estimate mu for different shapes. So, and here For example, for open ditch trapezoidal cross section, so U is, so this is the trapezoidal cross section. So, B is the the width, and then this is the depth y and the slope, right, z. So, in that case, so U is equal to B plus 2 y and square root of z square plus 1. So, this is the U, okay, this is the U perimeter. The pipe drain in trench, suppose a trench contains a pipe drain, right, a pipe drain is a trench, then U is equal to, if this is the B and if this is R naught, okay. So, here you get R naught plus R naught, so that is 2 R naught. So, U is equal to B plus 2 R naught. The pipe drain surrounded by envelope, suppose you have a pipe drain which is surrounded by let us say the envelope, right. So, in that case U is equal to B is the width of the trench, right, which width of the trench, and 2 into 2 R naught plus m. So, m is the height of the envelope over the pipe. So, height of the envelope over the pipe, this is m. Okay. So, this way you can estimate the U value, that is weighted perimeter for different conditions. And then what about A d square, right. So, A, so it is the function of solve profile and position of the drain. So, these two things, solve profile as well as the drain position. So, drain in the bottom layer, if the drain is at the bottom layer, then A is equal to 1. So, bottom layer, since radial flow is restricted to that layer. So, since there is no radial flow, radial flow is restricted, A will be 1. If the drain is in the top layer, the value of A depends on the ratio of Kb and Kt. So, Kb is the top layer hydraulic conductivity, Kb is the bottom layer hydraulic conductivity. So, suppose you have the two layers Kb and Kt, right. If the drain is installed on the top layer, drain is installed in the top layer, and you have that depends on Kt and Kb, you can estimate the A value. Okay. A depends on Kt and Kb, but whereas if the drain is at the bottom layer, suppose here, right. So, in this case, so the mostly the horizontal flow is influencing, and radial flow can be is independent of the radial flow, won't be an issue here. So, A is equal to 1 in that case. So, let us see the second case, that is drain is installed in the top layer. So, in that case what happens if Kb by Kt is less than 0.1, the bottom layer is considered is impervious, okay. And then so the solve profile becomes one layer and A equal to 1. So, mostly if Kb and Kt is less than 0.1, so that means the top layer has less hydraulic conductivity, or sorry the bottom layer has. So, suppose Kb less than or equal to 0.1 times Kt. So, that means bottom layer has impervious surface, impervious layer, and the solve profile becomes one layer. So, then A is equal to 1. So, but 0.1 Kb and the next one is here Kb is greater than Kb by Kt greater than 50. So, that means Kb greater than 50 times Kt. So, it is more pervious, then A is equal to 4. So, in between 1 and 4, right, in between 1 and 4. So, we need to A is equal to 1 and 4 can be estimated like 0.4 it all depends on the ratio between 0.1 and between 50. So, it decided Kb by Kt and dB by dt. So, that is aquifer depth or aquifer thickness of the bottom layer, thickness in the top layer. So, using relaxation method or nomographs, these two things can be used to find out the A value. So, let us see how we would find out the A values based on Kb by Kt and dV by dt. Here there is a table which is called relaxation method table. So, Kb by Kt values are here and dV by dt values are here, and the corresponding the A values are for example, the kV by kT is 10 and dV by dt is 4, right, and the corresponding value is 4.2. Okay. And then there is a nomograph also available. So, here for example, this is the the drain installation. So, the drain is at the top layer, okay, drain is at the top layer, and K1 the top layer hydraulic conductivity, K2 bottom layer hydraulic conductivity, and D naught this is so this D2 is dB, right, D2 is dB and D naught is dt. Okay. So, this is dt and this is dB. So, d2 by, so this is dB by dt in our case, right. So, here what happens, so K2, this is K2 by KT by KB, sorry, KB by KT, right, KB by KT. So, knowing the KB by KT value here, okay, and then see this is dB by dt values, these curves are, these all curves are dB by dt values for a particular these curves. Okay. So, just knowing the knowing the kB by kt and dB by dt. So, then you will be finding out the point where it is going to intersect, and from there just project onto the y axis, right. So, that will give the corresponding A value, okay, that will give the corresponding A value here. Okay. So, this way you can estimate the A values. Okay. And so, from this graph, this is a combination of all the things. So, this graph L can be determined from the nomograph using Ernst equation. So, when D naught is less than L by 4. So, D naught is what? This is the top of, D naught is here in our case, which is this is so D naught is dB dt, okay, D naught is dP, D naught is dt. So, knowing the dt, now if the dt is less than L by 4, so L can be estimated using the following nomograph. So, here if you observe this nomograph clearly, right. So, one axis, so this y axis is h by q, right, if you refer to the Ernst equation. So, the Ernst equation will be this, okay, this is the formula. So, in this, so y axis, one y axis has sigma k d, the other y axis is h by q. So, these are known values. Okay. So, knowing these two, you just draw a line combining these two, okay, and these are all the W r lines. So, where W r is 1 by pi k r into ln of A d r by mu, right. So, now see, after finding W r, okay, so then the corresponding you just project it onto this line, this is another sub axis line, sub x axis line, and that will give the L value. So, that will give the L value. So, in using Ernst equation, you can find out the drain spacing by knowing the Kd value, right, sigma Kd like K1 D1 plus K2 D2 something like that, based on the number of layers, and HQ H by Q value, right. So, then WR. So, these values will be known, and based on that you can find out the drain spacing. Yeah. So, thank you. So, this is all about this lecture. So, in this lecture basically we solved some example for Hooghoudt equation using the trial and error method. Okay. So, we used both theoretical base like the analytical method as well as the graphical method in order to find out the drain spacing by knowing certain soil parameters. And then after that we move on to the equivalent depth formulas and then Ernst's equation. So, in the Ernst equation, so how to find out A and mu, okay. And then I mean using the nomograph you can find out these values as well as for the two layered system. And finally, by knowing the knowing the h by q, right, sorry, q by h value, and then w r and also the sigma k d, you can find out the drain spacing drain spacing. Thank you.